Hello everyone and welcome. Agentic AI is moving rapidly from experimentation and enterprise deployment. But with intelligent agents making autonomous decisions managing business processes comes cost and performance risks. Today, I will introduce a practical framework for cost optimization and performance control of agentic AI systems, ensuring meeting business processes performance requirements at the lowest cost. Let's begin with what is happening in agentic AI world now. Agentic AI has moved beyond experimentation and proof of concept. In 2025, for example, most organizations were running piloting projects with just a few agents managing business process. Now, we see that the number of intelligent agents managing business processes in complex multi-tier agentic environment is growing exponentially. By 2027, enterprises plan to deploy thousands of agents. This creates enormous business opportunity, but causing the unpredictability in performance and runaway spending. To optimize cost and control performance, we need to understand the architecture of these complex agentic AI environments first. The architecture of agentic AI systems is multi-layered, and every agent request touches multiple components including orchestration, LLM reasoning, tool execution via Model Context Protocol (MCP), and retrieval augmented generation (RAG), which combine retrieval from external knowledge sources like vector stores with generation capabilities of large language models (LLM). It provides more accurate, relevant, and up-to-date responses. When agents use local resources, the response time is better comparing with cases when agents use common LLM, RAG, and MCP servers. In these cases, each layer introduces variable latency, changing cost, and operation variability. This multi-layer complexity is exactly why traditional monitoring and FinOps, DevOps approaches break down. Autonomous intelligent agents are managing the business processes. For example, claim adjudication, fraud detection, production scheduling, patient monitoring. Each agent plays a specific role and has memory containing the frequently used context. Agents make independent decisions and use different tools to perform actions in managing business processes. And primary goal of managing and tuning agentic environment is shifting from optimizing specific queries and maybe selection LLM models to optimizing autonomous decision-making systems. The governance of agentic AI is done at two levels. Inside of each agent, the micro level control guardrails, retry limits, and safety enforcement. Across the system, the macro governance set workload priorities, service level goal enforcement, and cost control. That leads directly to the need of the closed-loop performance and cost control. Agent lifecycle includes data preparation, making enterprise knowledge AI ready, then building the agents, deploying agents, and governing agents in production environment. The cost of continuously meeting business process service level goal is escalating, and there is a need for automated observability and decision optimization during all phases of an agent life cycle. And the most important goal is to organize the closed-loop cost optimization and performance control. Agents never sleep, and depending on the changing business process conditions, agents use additional new information to determine the next action required to manage business process effectively. Autonomous behavior in increasing number of agents affect agents' performance, and cost explode unexpectedly. The manual governance of this environment becomes impossible. So the only viable approach is implementing closed-loop feedback control, which includes automation of observability, use of modeling optimization, and adjusting agentic configuration and workload management rules. First of all, observability in the complex dynamic environment should be automated. We cannot rely on humans to interpret thousands of agent traces. We need automated telemetry, data collection, workload characterization, and layer-specific profiling, performance profiling, resource utilization profiling, and observability is not optional. It is the foundation for governance. Four categories of metrics are important for monitoring agents and agent infrastructure. First of all, performance, which include latency, throughput, and tail response time. Then cost, tokens, credits, API spend. Resource utilization, utilization of CPU, GPUs, memory, storage. And agent behavior, number of retries, reasoning depth, and tool efficiency. These metrics define whether the system is stable or spiraling. This slide is important for executives. It shows that response time fluctuates across different layers of the infrastructure. For example, orchestration decision can take seconds. LLM calls take up to 10 seconds. And using tools can add unpredictable delays. So the agent total response time is the sum of response time of different components across layers. And the goal of the governance is to ensure that the total response time, agent response time, always below the business process service level goals. Cloud data platforms are used as a base for agentic AI infrastructure. And each of these platforms can support agentic AI service level goals, but with very different cost. They also expose very different types of measurement data. For example, Snowflakes provide Cortex telemetry. Databricks provide system tables and ML flow tracing data. Teradata has exceptional measurement data, including information about CPU, GPU utilization. BigQuery integrates with cloud monitoring. So platform choice directly impacts your ability to organize observability and govern agentic workloads successfully. Snowflake Cortex provide a lot of valuable measurement data. It is a fully managed agentic AI stack. It exposes agentic infrastructure performance and cost measurement data, but does not report information about resource utilization. In general, it is valuable for enterprises seeking governance with minimal operational overhead. Databricks approaches observability through engineering control. Databricks system tables, ML flow tracing, Unity catalog, governance provide a lot more measurement data than Snowflake, but it requires more efforts to integrate measurement data and organize effective governance. In order to compare different options, some of the organizations relying on observability data collected during the benchmark tests. In general, benchmarks are useful for addressing specific capability questions. For example, the benchmark can answer questions like, can an agent solve specific task? But organizations also need to answer two different questions like, can agents solve this task reliably at scale within the budget? In order to compare options and address many what-if questions, the modeling optimizations are needed. Queuing network models and gradient optimization help to evaluate different options and answer critical questions like how agents will perform after deployment and what will be the configuration and cost needed for agent to meet business process service level goals. What will be the minimum configuration and cost needed to meet service level goals when the number of agents and agentic workload will increase? Or which agentic platform is the most cost-effective for our specific workload? And when agents are in production, how to optimize dynamic capacity management decisions. So the modeling and optimization turn governance of agentic AI into an engineering discipline. Let's illustrate modeling approach using simple example of applying open queue network model to predict the response time for growing workload during next 12 months. We apply queue network model utilization and response time lows, and when the server utilization is close to 0, the predicted response time is close to service time. Service time is equal to 0.3 seconds. As arrival rate of workload increases with rate of 20% per year, the utilization increases linearly, but the response time increases exponentially. According to prediction, the current configuration will fail to meet 2-second service level goal within 8 months. So if we increase the server configuration to reduce service time from 0.3 to 0.25 seconds, the response time will reduce and become below service level goal till the end of the year. But the question is it the minimum server configuration needed to meet service level goal? So we can apply the same model to determine the minimum configuration service time needed to meet service level goal. This is a simple example illustrating optimization process. In reality, we use more complex closed queue network models. These models have powered capacity management for decades. Now we adapt these models to multi-layered agentic systems. In agentic systems, intelligent agent generate requests circulating across layers, visiting different components of the system multiple times, which affect performance and cost. Let's review an example illustrating that. This time diagram shows an example when 3 agents working concurrently manage the same business process, which has 15-second response time service level goal. Each agent request are processed by different layers and different components of this multi-layer architecture. And they have different response time. And the response time of each agent is different, but overall, all these agents meet the 15-second service level goal. Queue network models work in tandem with gradient optimization. The objective is to determine the minimum configuration and workload management changes needed to meet service level goals. Work is organized by multiple steps. During each optimization step, the algorithm changes the hardware configuration and workload management parameters, and model predicts performance of each agent running on different components of each layer and predict the total response time. An optimization process repeats many times until the predicted response time meets service level goal. Modeling optimization apply to evaluate options and recommend the most appropriate platform type, minimum configuration, and workload management changes needed to meet service level goal with the lowest cost. The same technology, modeling optimization technology, is used to size new agents prior to deployment, used to implement dynamic capacity management production environment, and to organize a closed-loop cost optimization and performance control. Let's review several examples illustrating the value of this technology. In general, any platform can meet business process service level goal, but at which cost? Modeling optimization uses observability results characterizing performance and resource utilization by each agentic workload, business processes service level goal, to compare the cost needed to meet service level goal by each optional platform. It provides a quantified comparison before committing to a specific platform and its configuration for multi-year contracts. As a first step in selection of the appropriate agentic platform, organizations can rely on selection metrics presented by industry analysts. This metric summarizes each platform's strength. For example, Snowflake, its governance and workload isolation. For BigQuery, elastic bursty environments. For Databricks, engineering-heavy pipelines. It is a premier choice for data engineering teams that require high performance, scalability, and code-based control over their ETL, ELT processes. For Teradata, it's mission-critical, high concurrency applications with requirements of detailed observability. Azure Synapse and Oracle, it's ecosystem-driven governance. Application of modeling optimization, on the other hand, based on specific agentic workload, ensures SLG service level goal-driven selection, not just selection based on marketing recommendations. This slide shows predicted response time for medium-sized and large agents during next 12 months. We can see that medium-sized agent will not meet service level goals starting August, and long size or large size agent will exceed service level goal even earlier. That's a problem. On the bottom of the page, we're showing results, modeling results, determining the minimum configuration needed to meet service level goals till the end of the year. This example illustrates the value of proactive capacity management instead of reactive firefighting. This is an example of comparing the minimum configuration and cost needed to meet the business process service level goal during daytime, evening, and nighttime during next 12 months. And the first table shows the minimum configuration which needed, and we can see that each platform can meet performance service level goals. But the second table shows the difference in cost required to meet service level goal. And as we can see, the cost difference is really dramatic. So predictive modeling enables quantified cost performance comparison, not just guesswork. During testing of new agents, the observability process collects performance and cost measurement data. These observability results feed the model, and model determining the minimum configuration and budget needed to meet service level goals before deployment of new agent, new applications in production. The first graph here shows the predicted minimum Snowflake configuration, and the second graph shows the budget needed for new workload to meet service level goal during next 12 months. This prevents the performance surprises and budget overruns after deployment of new agents and new workload. It helps to set realistic performance and cost expectations. And sizing of new applications becomes engineering, not just trial and errors. Once deployed, agents and agentic workloads evolve because the number of users is increasing, the number of installed agents is growing, and the agent's behavior changes depending on changes of the business processes they manage. So there is a need for dynamic capacity management in order to continuously meet business service level goals with the lowest cost. When observability process determines performance and cost anomalies and corresponding root causes, the performance tuning is the first level of defense. We can reduce idle time. In general, warehouses waste about 20–25% of the credits. You can reduce data spill and improve execution efficiency. You can optimize top cost drivers focused on dominant agent and workload. Or you can manage seasonal peaks by allocating corresponding resources proactively. Another performance management opportunity is to change workload management parameters and resource allocation rules. All these deliver measurable savings quickly. Traditional budgeting relies on historical spend, but agentic AI requires service-level goal-driven methodology for budgeting. Modeling determines the minimum cost needed to meet service-level goals for existing and new agents and workloads, which take into consideration expected growth in number of agents and number of users. Modeling results set realistic performance and cost expectations, and budgets become predictive, not reactive. Budgets represent one of the components needed for organizing closed-loop performance and cost control. Micro and macro control of agents in agentic AI environment needs coordination and automation of governance. Automation of observability, modeling optimization, and action automation is a foundation of the closed-loop performance and cost control. It includes comparing actual results with predicted, detecting most frequent and severe anomalies and their root cause explanation, organizing and developing corrective recommendations. All of this is a foundation of continuous governance, not just periodic reporting. To conclude, agentic AI is moving rapidly into production, and it is reshaping enterprise workflows. But it also introduces a fundamentally new challenge. Cost and performance become nonlinear and unpredictable as agents scale. Traditional FinOps and DevOps framework provide observability, but they do not provide the predictive control needed for autonomous system. The path forward requires three pillars: automated observability, predictive modeling optimization, and closed-loop control. This is how organization can consistently meet service-level goals while avoiding runaway spend. This is exactly what B is Next delivers. Thank you, and I would like to open the floor for questions.